Yeah. Have you? Okay, I think we can move on, right? Great. Okay, so yeah, thanks to, well, especially Kiryl for coming here to tell us some interesting stuff he's been doing. He's been working for a number of years already about various kind of general frameworks for constructing non-ergodic states, and he will tell us about, I guess, about some realizations of that in multi-band fermionic models. So please go ahead.
Thanks for the introduction and for the invitation. It's always great to be in person, and also everything worked quite smooth today. So indeed, I'll tell you about the multi-band scarce and multi-band fermionic models. Okay, so one thing to remind you quickly about ETH, one thing to think about it is that if you have some observable in your system and you measure it in every eigenstate, then and you plot the result as a function of energy, you should be getting something, some sort of smooth curve, and all the eigenstates should more or less follow that curve. And many body scars, one of the definitions is that they are outliers, so they are far away from that smooth curve. And then since it's a non-equilibrium seminar, this is a teaser for the time evolution, what we're going to see. So we're going to prepare a state that is not an eigenstate, and we're going to take an non-integrable strongly interacting Hamiltonian, resolve all the symmetries, and prepare a state that is not an eigenstate of the Hamiltonian. And it will also correspond to some high temperature state, or be, in other words, somewhere in the middle of the spectrum. And then we let that state evolve, and we watch the overlap between the original state and the time evolved state. And of course, what we expect in an ergodic system is that very quickly the overlap goes to zero and basically stays around zero forever. And why is that? Because in an ergodic system, there will be matrix elements connecting that state to pretty much everything else in the Hilbert space. And of course, this will decohere your state very quickly, and the information will be lost completely pretty quickly. And so what happens with the scars is that you will see repeatedly the system coming back to that exact state that you started from. So what we know, here is a small summary, what we know about many body scars. And some of this work is due to Zlatko, as you know, I guess. So first they violate ETH, which is cool. So then they can be anywhere in the spectrum. In particular, they can be at high temperature in the middle of the spectrum. In a lot of cases, I guess in most cases, they have low entanglement. In that sense, they look like ground states, although they are far away from low energy. And this time evolution thing that I just told you, and this is the experimental curve. If you start with, if you initialize the system to a mix of scars, then you will see oscillations that in the original experiment, they couldn't explain. Why is that? Now we know that if you have exact scars, you will have this probability coming back to 1 forever. And this is, well, an interesting new feature. So what's interesting, besides violating ETH, which is a fundamentally new physical insight, maybe, hopefully, we could also use it for quantum computing applications, because when you initialize your system to some pure state, essentially you are putting in some quantum information, and then it comes back to you almost forever, moreover, in a state that corresponds to high temperature. So maybe we could, at some point, build some high temperature quantum memory, my dream, out of this. So now I'll tell you about how we make Hamiltonians that have these states. And one fact to remind ourselves about the invariant states under some symmetry. So if we take some symmetry, and this is an example for SO3, special rotations. So if we take a state that is invariant under a symmetry, then it is exactly annihilated by generators of that symmetry. So if we take rotationally invariant state, it is annihilated by the generators of rotations. And that is true for other groups as well. And this is what we will use in our recipe, which is on this slide. And basically, if you want to take away just a couple of the slides from my talk, then this will be one of them. So how do we make these Hamiltonians? Basically, we need, well, let's first look at the full Hilbert space. This is this blue circle here. And then let's find in the full Hilbert space a subspace, the green subspace of states that are invariant under some group G. And then let's take the Hamiltonian of this form, where H naught is something very simple, maybe a constant I'll explain later. And then T is a generator of this group G. And we just agreed that it will annihilate the green states because generators annihilate the invariant states. So essentially for this Hamiltonian, what we have that only H naught part acts on the invariant states, and the full Hamiltonian, which can be made quite chaotic by the choice of this O, which is quite free. There is almost no restriction how you choose the operator O. So the full Hamiltonian can be made quite chaotic. And there you go. You have two different Hamiltonians acting on the different subspaces, and therefore you expect indeed different properties for the states in the two subspace.
For singlet?
Yes. Which is invariant basically under the group G. Okay, so this is the recipe. What do we want from H naught? Basically, the only major requirement is that it should mix invariant and non-invariant states. And so the scars, the singlets here, they should be eigenstates of H naught. And if you want to see the revivals, then basically what you can do, you can write down the overlap of the original and the time evolved state and realize that if there is a common divisor to all the gaps between the states in the green subspace, then you will have actually this overlap coming back to one repeatedly, just as a result of constructive interference. But the case that is realized so basically common divisor doesn't mean all the gaps are equal. But in most cases, we know from literature, actually it's a tower of states where all the gaps are equal between all the green states. And this you could achieve by, for instance, splitting some magnetic multiplet with a B field. So the cartoon view of this is as follows. So if you don't put this additional requirement on H naught, then you have the picture on the left. So you start anywhere in the generic subspace and you do your time evolution and you bounce inside, never entering the invariant subspace, and you explore fully your blue subspace. If you start anywhere in the green subspace, you also bound inside the green subspace and you explore the full green subspace, but you never mix with the blue subspace. However, if you add the additional condition on H naught, that creates sort of a closed orbit inside your green subspace, and your time evolution takes you along this closed orbit, and then you come back to your place where you started from in the beginning. Okay, so the simple sort of example is when you have spinful electrons sitting on a lattice, and for us it will turn out that the dimensionality of the lattice doesn't matter so much. And the observation, if you look at, so the question to that recipe, how do we choose this group G, right? We need the states invariant under the group G, so what group do we choose? And one observation we made quite, well, accidentally, I would say, was that if you look at the Hawking, then you realize that actually it forms a closed algebra. And so why not take the group that corresponds to that algebra? So that was our motivation, although this is by no means the right way to go. And if you have other ideas with what group you want to choose, that's totally valid too. But we went this way, and so then we realize if you commute all the terms, all the hopping terms, then they close. And then the question is to find out what group it is. And then turned out that it's this special SO group where n is the number of lattice sites. So essentially you commute all the lattice sites, and this is the symmetry. You're allowed to do any kind of permutation of the lattice sites. Sort of. And then it also turned out that my collaborators studied the same Hilbert space, and Hilbert space is central here. I haven't told you anything about the particular Hamiltonian even before we thought about scars, and they found this interesting fact that in this Hilbert space of spinful electrons on a lattice, the representation of this ON group is actually strongly bound to the representation of two SU2 groups that also naturally act on your subspace. And these two SU2 groups may be familiar to you from SO4 symmetry of the Hubbard model. So basically one of them is the spin SU2, the regular spin, and the other one is the pseudospin. And if you say that I want states to be singlets on the ON, then it automatically gives you only two possibilities for this SU2s. Either it's also invariant under one of the SU2s and then maximum spin on the other one, or the other way around. So as you see here, the two options. And that is actually what helps us to construct the actual wave functions, because we want the singlets, and actually constructing singlets of ON is maybe tricky, but constructing singlets of SU2 is easier. Yeah, so this is a reminder what the SU2 the pseudospin generators are. But then you can actually go ahead and construct those wave functions. And here are some formulas how you construct them, but later I will also give you a more physical interpretation of what they are. But interesting fact is that in 1989, C and Young already wrote down exactly the same wave functions because he was looking for excited states of Hubbard. So he wrote down exactly the same wave functions, and he also found this interesting property of these wave functions, that there are certain correlators that do not fall off in space. So you measure them at different positions and they do not fall off. And moreover, they are of this C-dagger type. So you kind of have sort of pairs, Cooper pairs. So I'll expand on this in a sec. But the physical interpretation of these states is as follows. So the lowest state is just vacuum. You don't have anything anywhere. And then you take one pair of spin up, spin down, and you place it on all possible lattice sides that you have. And you take equal superposition of all these states. So this you call the first state. And then you now take this first state, and now you look where the empty places are, and now you put another pair in all possible positions that you find empty, and now you take again the equal superposition. And this is your second state, and then you continue until you filled up the whole thing. So this is what I like about these states is that they are not totally crazy. So we started from just requiring that they are group invariant, but they also have this meaningful interpretation. And now these correlators, so this is, there are two families of states, but we can maybe focus on just one of them, the eta states, the eta-pairing states, also known as. And then there is this correlator that doesn't fall off with the distance. So you kill a pair of spin up, spin down on side J, and then you create it on side I. And this correlator evaluated in any eta state, it doesn't depend on I minus J. So C and Yan was already excited that it doesn't fall off quickly with I minus J, but actually we can show that because of this ON invariance, it actually doesn't depend at all on I minus J. And well, it sort of makes sense because ON is the group that lets you shuffle all the sides. And if your states are invariant under this shuffling, then of course it shouldn't depend this correlator on where you create or kill the pair. All right. So now talking about the Hamiltonians, we want them to be of this form H0 plus OT. And maybe you're thinking it's only some crazy Hamiltonians that you can have. But actually, we took the Hubbard interaction and we showed that it does decompose into the form that we want. And so here I write down two ways of decomposing this because there are two choices, natural choices of this group that you can have. And in both cases, you see that we have here not OT, but we have TT. So we have actually generator squared instead of choosing some crazy random O, we have just TT, and M here in one case is just magnetization squared, and the other case it's just 1 minus magnetization squared. So it's quite simple for Hubbard once you've decomposed it. Of course, it's quite hard to take a Hamiltonian and ask yourself, how do I decompose it into a product of some operator? It's much easier to take two operators and calculate their product.
What's the Q, sorry? What's the Q?
Total number of particles, and N is the total number of sites. So basically, this is the point. The H0 part, the green box here, is just a constant. And of course, it creates very simple spectrum in the invariant subspace.
User has two scars.
Yeah, so it is of this form that we want. So scars, it supports scars. You can add other things to it, which are of this form, and the scars will still be there. This is the point. Then you can also play the same game with Heisenberg and figure out that it also has the composition that we want. And now we can combine the two. And this is what we did. Basically, you can study this TJU model, which is Hopin plus Hubbard plus Heisenberg. And since every term in the Hamiltonian supports scars, then also the linear combination does. And then we looked at all this bunch of other models that are in some way a combination of the terms I just told you about, and found that, and then just, checked which, there are actually 3 families. I told you about 2, but there is another one. And checked which family is supported by the Hamiltonian. So as you see, they are not some crazy Hamiltonians. They are quite normal Hamiltonians that we all know. There is one sort of hook that I haven't told you about yet, is that, of course, this phenomenology of scars would be trivial if they sit in an isolated sector of symmetry, right? So if your Hamiltonian has a symmetry and you start anywhere in the sector, of course, you don't exit the sector. So this is sort of a trivial thing. And this is what happens in Hubbard if you take pure Hubbard, because this states, they happen to be completely filling up the sector of the maximum spin of one of the SU2s, and Hubbard respects that SU2, and so they are in a separate sector. So it's sort of trivial. What makes it non-trivial is that now to Hubbard we can add any OT that we want, and we can have O that will break all the symmetries of the full Hamiltonian, but the scars will still be there. This states with huge symmetry, ON, and the N is the number of sides, they will still be in the Hamiltonian that has no symmetries at all. So basically this is it. We have written down all the generators that can be used to build this Hamiltonian. So essentially now we hope that everyone can take these building blocks and build the Hamiltonians to their liking and know that there will be scars.
So what determines which family of scars you have for the different models? Because you said it was just a property of the group.
Yeah, so they all are invariant under a slightly different group. And then you take your Hamiltonian, you decompose it, and you see that you are either able or not to decompose it in the H0 plus OT form for that group. And if you are able, then they are there. If not, then not. This is the point. And some Hamiltonians you are able to decompose as H0 plus OT for different groups. And that's why more than one family can show up for that interaction. And then you can do some numerics to actually test if everything works as planned. So we took this TGU model, which is again Hopin plus Heisenberg plus Hubbard plus this OT term that we just put in by hand, where we choose something quite crazy that just kills all the symmetries basically. This is just for the numerics to see this nice thermal curve and know that all the symmetries are broken. And then you can see that, yes, indeed, there are these states at low entanglement that we can actually construct. Since we have the wave functions, I can just construct them by hand and really calculate the overlap and see that these are the states. Then what we can also do, we can do the gap histogram for the bulk spectrum for these thermal states here, and see that it does follow basically a random matrix, what you would expect from the random matrix. So the full Hamiltonian, so we have TGU plus OT, where O is very chaotic. So the full Hamiltonian, because of this OT, it became the bulk, most of the states, they became thermal. Yeah, and this you can see in this histogram of the gaps calculated for most of them. And then you can see that the entropy is really high for all of them. But nevertheless, there are hidden in the spectrum these excited states that are scarce, that stay at low entanglement. And then you can also do the time evolution, so you can initialize your system to some mix of these states and let it time evolve and see that it does come back to exactly where it started from. And so the time period here is determined by the common divisor of all the gaps between all the states, the scarce states. But then there are also subsets of states that have a common gap. And then here you have like smaller amplitude revivals, but that's technical, small detail, not so important. So now one interesting feature of the states, I'm telling you about low entanglement. So let's remind ourselves, how do we calculate entanglement entropy? So we take our state that lives somewhere on the lattice, and then we cut it into two pieces, subsystem A, subsystem B. And then we are trying to take our state and do singular value, or also known as Schmidt decomposition of the state. Yeah, so we have part of the wave function that lives only on the subsystem A, part of the wave function that lives on the subsystem B, and then we have the singular values here. And then we calculate the entanglement entropy by, well, this formula, taking this singular values. So what values can it take? If we only have one entry here in the sum, then you will have 0. And basically you will have a product state. And that makes sense. So product state, 0 entanglement entropy. So what's the maximum entanglement entropy you can have? This happens when you have all of the singular values non-zero and equal to each other. And then essentially the entropy becomes logarithm of this Hilbert space dimension of your subsystem A. Okay, so this is the bound on the entanglement entropy of any generic states, including the thermal states. Now, yeah, so basically this dimension of the subsystem is what determines the bound. And if we have just spin 1/2 electrons on lattice, then this is this dimension. Now, we have an argument why the group invariant states that we design following our recipe, why they have reduced entanglement entropy always. And the idea here is follows. If we cut an invariant states, then we get two pieces, and the two pieces will also necessarily be invariant. Because the group we chose in the beginning, it mixes all the sides. So of course, if the whole thing needs to be invariant under the arbitrary mix of sides, then also if I cut it in two, then each half also needs to satisfy the same property. And that means that when you cut in two, you cannot, there are only special states that can contribute to this decomposition here. Not all of them. So the sum here now runs not to dimension, full dimension of the subsystem A, but only to the number of these special states that you can build in the subsystem A, right? And this basically tells you that here, instead of the maximum entropy you can have is log not of the full dimension of the Hilbert space of the subsystem A, but the dimensionality of this invariant green subspace from one of the first slides. And basically this holds true for any invariant states built to our recipe. So this was sort of a recap of one band. Now I'll go to multi-band.
So that means that it's still volume law? The upper bound is volume law?
Why volume law? So it's a logarithm of dimensionality of the.
Yeah, so that's some exponential event.
Well, this actually it's group specific, right? So you choose a group and then you ask how many singlets do I have for that many lattice sides. So it's not obvious what you have here, right? So if we go back really to the beginning, it's how many states you can have here in a system that is half the size. In the subsystem A, how many invariant states do you have here? And normally this is much lower than the dimension of the full subsystem A, right? Because this would be, so this is the point.
But is it exponentially large in N1 or something smaller?
Well, we'll get to this for the one of the examples. But basically, no, this is not the volume law. So now,
that would be interesting, right? Have like a smaller volume law, like it used to be.
I wouldn't be able to answer right now because there are so many groups that you can think about.
You need to choose some very weak group, right? Like
Small one, yeah.
Yeah.
I'm not sure. So now the multi-band, there are several ways to think about the multi-band. In principle, and this is most of today's talk, I will be talking about this when we take multi-flavour Majorana fermions. So we have site index and we have some flavor index. And this is already multi-band fermionic systems. In principle, you can also say that you want complex fermions also of different flavors. Or you can want to have complex fermions that have flavor and have spin 1/2. So I'll tell you a little bit about this too. And as you can imagine, of course, the more structure, so as you go from left to right here, you have more structure because here you already coupled your Majoranas. Of course, you can always think of complex fermions being built from Majorana fermions like this. But here you already coupled them in a specific way. And here you also specify that some of them represent a spin. So as you go from left to right, you increase the structure, and that actually increases greatly the number of meaningful groups that you can have in our recipe. But for the first one, so when we have multi-flavour Majoranas, so then natural group acting on this Hilbert space is SON cross SOM, where N is the number of sites, M is a number of flavors. And now as a group G, we will choose this SON, which is the same basically motivation as before, the group that mixes all the lattice site indices. And the generators that we'll choose will again be the hop-in. So same approach as before. So now the generalized eta states, remember these states I showed you where we take the spins up and down and we put it in different places. So now we will have to generalize this a bit. So first we write down the generators for SON, SOM. And then remember that plot that I showed you, that representations of ON group are coupled to the representations of two SU2s. So analogous statement here is that quadratic Casimirs of these two groups actually sum together, they give you a constant. That means if I want singlets on SON, that means the Casimir there is 0. That fixes the Casimir for SOM. And effectively, that means the same, that representation of with respect to SON is fixed to a representation coupled to a representation of SOM. Okay, and then basically what we do, we find the raising operators of this SOM, and we find the lowest weight states. And now to build the invariant states, we just act with this raising operators on the corresponding lowest weight states. But all in all, it looks maybe a little puzzling, but all in all, it looks very similar to what we had for the eta-pairing states, because there we also took the vacuum and acted with an operator which looked very much like this, except that there was only spin up and down that we could use, and now alpha and beta, beta and gamma, they run through more flavors. So there are more combinations you can have here, and each combination actually gives you a valid invariant state. But all in all, that's a similar story. And yeah, so basically you can have your green subspace factorizes into the direct sum of two families of states, H eta and H zeta, each built by acting with either this raising operator or this raising operator on these two sort of vacuums. Okay, so now we come to the dimensions. And basically, this is the dimension of the green invariant subspace as a function of M, the number of flavors. So if we have 4 flavors, which is the same as spin 1/2 system, then we just have a number of sites plus 1 states. So then if we have 6 flavors, then it's already this binomial coefficient, and then you see it grows. And then we have an ugly formula, which I don't show you for more general case, but then you can take some asymptotic expansion, and then this is the bound that you are asking about, that you are getting. So it's logarithm of the number of sites in the subsystem A, and then you have the number of flavors here. This is the bound for the entanglement entropy of this green subspace.
Can you, can you do me the example M equals 4?
M equals 4 is actually exactly what we talked about the first part of my talk, because this is M equals 4 means you take 2 Majoranos to make spin down and 2 Majoranos to make spin up. So this is the 4 flavors.
That's why it's N plus 1.
Yeah, and there we had N plus 1 states. So everything I showed you in the first half was exactly the example for M equals 4. So now this also looks scary, but I'll tell you, I'll convince you, hopefully it's not. So this is, you'll get to this if you take your normal Hubbard Hamiltonian and you just ask yourself, how do I write it down in terms of Majorana fermions? And this is what you will get. So you will get, well, this is just some constant, not important. This is just chemical potential. Then this is the Hubbard interaction. So it looks a little scary, but remember, Hubbard interaction, it takes density of spins up multiplied by density of spins down. And here, since we have more flavors, we had to generalize it somehow. So we multiply all the flavors that we have, not just spin up, spin down, but also other flavors. And you can also notice that this Hubbard interaction is actually a SON invariant. It's of course not obvious to you, and wasn't obvious to me for a long time. But if you want to think if an operator is ON invariant, basically it needs to be treating all the side indices the same way. This is sort of the hand-waving rule of thumb how to tell this. And here we see that indeed it doesn't do anything special to the any selected site. So it's blind to whatever site you choose. But since it's SO invariant, it means it's also H naught in our scheme. So this part of the Hamiltonian actually not in the OT, but it's in the H naught part. So then we have the hopping term, also not scary, and then we have here something ugly of the OT term type, which we just add to break again all the symmetries that we didn't want to have. So this is it. This is the Hamiltonian, but the take-home message is that's just the Hubbard in the multi-band case. So what are the features that are new now when you have multi-band? First, you have many more scars. So this is the m = 4 or spin, single band spin. Yeah, so here we had just a little bit of scars, just a few. Now we have many more of them. You also notice that in general, they are not equally spaced, and you don't see any like common divisor between the energies. But it's possible to choose the chemical potentials such that you have revivals. So there will be a common divisor, and there will be revivals within this huge space of scars. So then there are some. That's an interesting feature.
A lot of structure here, right? We're not celebrating it that much.
A lot of what?
The scar state.
Yeah.
There's a lot of structure in something like that.
Well, I think you can think of them as a tower of towers in terms of spectrum. So before we had just a tower.
These states are very particular entanglement problems, right?
Well, they are generated in a very particular way. So you have
entanglement problems are very exact, yeah, very specific.
Sort of.
You get these straight lines, I guess.
Yeah.
Are those like log 2, log 3, or nice?
There is definitely log 2. There is also a bunch of product states.
No,
Yeah, to be honest, I haven't calculated for all of them. Like, haven't really looked what they are, but there must be some of them.
last one's probably about 29.
Yeah, well, we could look later in more detail. I don't remember.
So also this subspace, is it like chaotic? Like it's at the level.
That's the next slide. This is actually the question that Zlatko asked last time when I had preliminary slide about this, and now I have the actual answer. All right. So what else I wanted to say? Yeah, unbreakable degeneracies. So basically, well, we see that inside this invariant subspace, some states are degenerate exactly. And we were trying hard to get rid of these degeneracies, and then we found that actually they look to be unbreakable. So this is the statement. First, the spectrum of all these states we know analytically, more or less. Analytically means you have some crazy Mathematica notebooks that gives you some answer in some not closed form, but we can figure them out for fixed number flavor. Now, if we want revivals, we just take chemical potentials to be well, one divided by the other, giving you an integer. So if you satisfy this, you have revivals. But now this is the statement. First, a very strong requirement. If your Hamiltonian fits our H0 plus OT form, this is already quite strong. But if you can satisfy this, then any local H0 cannot break this unbreakable degeneracies. So you cannot choose any arbitrary H0. It should be H0 that is from this form that we want. But once you've satisfied this, by any local term, you don't seem to be able to break those degeneracies. This is what we conjecture. We haven't proven this, but what we seem to find is that any local Hamiltonian just boils down to chemical potentials, and chemical potentials give you degeneracies. So this is what we think is the case. So, and then in in the abstract, I said that there might be some quantum information applications. And this is very hand-waving at the moment, but the idea is that when you have topological system, you have topological degeneracies, and then this forms your computational subspace, which is protected by the topology, by the fact that you cannot exit this degenerate subspace. So here you have sort of analogous situation where you, no matter what local H0 you choose, you also cannot leave this degenerate subspace. So you can, if you can make some operations that do transformations within the degenerate subspace, so then this is the protected, extra protected computational subspace for you. If it's practical in any way, I don't know right now. So now, if we can make this ergodic, the answer is yes. So this is basically corresponds to this cartoon picture where you start in your invariant subspace and then you move around in there, but you move around in an ergodic way such that you can explore the full subspace. Yes, this is possible. And then you get this nice ergodic curve here. And then if you plot the gaps histogram between only these states, then you get something here, which is only like 588 states. So it's not yet a nice curve, but it does look like emergent random matrix curve. So this is possible. There is one caveat that to be able to do this, we had to take something that was long range in this system. And it seemed to us that, again, and this comes back to this unbreakable degeneracies, that as long as you restrict yourself to local terms, you actually cannot break them. You cannot achieve this ergodicity. But if you allow long-range interactions, then you can have this. Maybe in other Hilbert space, the situation will be different, but here this seems to be the case.
So I guess one could ask, you know, can you do like a Russian doll that you now have another card outliers in the small subspace?
Maybe. Do you think that would be interesting? Of course,
that's
for
what I'm saying.
maybe, why not? But oh, we will see. Maybe I will give you the answer next time. Then just like with this one.
I'm a bit confused. So you're saying now that basically there's a big difference between local and non-local interaction.
Yeah.
But up until now, one of the points is that like you're kind of agnostic, right? You can have hoppings at a long range, right? Like the point is that you can swap open sites wherever you like. So where does locality come into it at this point?
Absolutely not obvious to me. So these states are indeed invariant under any, well, spatial transformations. That is true. Why we can only make them ergodic? Why can we only make the spectrum chaotic by using non-short range interaction, long range interactions? I have no idea. This is just the fact that we found. I don't have an explanation. And I don't, I'm not sure this has to be related. I don't know. There might be some deep reason behind this, or maybe this is just a coincidence. I don't know.
But did you really search exhaustively, or you just kind of went to this and saw it work?
No, when we were thinking about unbreakable degeneracies, what we tried to write down all possible terms that you can have as H0. So then the simpler ones, we were able to convert down to something that looked like chemical potentials. And the more complicated ones, they were already long range. So it seemed like we have these two choices. Either you go with something that is short range, but leaves some states degenerate, or you go to long range. So we did this half manually by checking in the finite systems, but it seems like if it did seem very plausible that as you go to larger system, it can only make the statement stronger. All right. So the next feature is this density of states. So the title of my talk, weak ergodicity breaking. Weak means there are only few of the states in the full Hilbert space, vanishingly small, measure zero. And measure zero means you never see them in the density of states. But it turns out if you have this multi-band systems and you take small systems like 6 sides, 6 flavors, 4 sides, 24 flavors, a little bit exotic, one could say, or 3 sides, 40 flavors, then which on the other hand could possibly be implemented in some quantum simulated, maybe like cold atoms. Then what you have that the green subspace is actually not so small. It's actually maybe like 1/3 of all Hilbert space. And so, and plus we know the wave functions, we know the spectrum analytically, so we sort of can move around these states in the spectrum where we want. So we can actually form the situation where all the low energy subspace is just scars, and they're not just few of them, but they are like really dominating the low energy. But this is only possible, it seems, for the small systems, but still is a little bit contrary to how everyone thinks about scars, because everyone usually is just a few states in the Hilbert space, but can be not so few. And now quickly about the other way of doing the multiband, when you have spinful fermions and you have also some band index. Maybe you have a material and then you have this XY orbitals, or you have some layers or something. So what we have here, this is a plot of different groups that naturally act on this Hilbert space. And I don't want you to like understand what each of them is, but I'm just showing this as an illustration that the situation becomes more complex. And in fact, any group depicted here, you can use as a group G in our recipe. You can say, I want states that are invariant under this SPN or UN tilde. And then this gives you a separate family of scars. And for most of them, we now know the generators, we now know the H0. So in principle, we have this toolbox also for this situation. So, and now the interdependencies. So if we take some finite system with just 4 sides and 2 bands, so there are a lot of ON invariant scars. And then if you make your group bigger, of course, there are fewer scars that satisfy this restriction. So basically, if we think about our work as producing these building blocks for, you know, everyone to take and build Hamiltonians that they are liking with scars. So with single band, you can only build simple things, but now in the multi-band, you have much more freedom to build more complicated structures. And well, basically, this is the summary, I think, yeah. So what maybe take-home messages? There is a lot of universality. So any Hamiltonian that you build according to our form H0 plus OT has scars. So scars are a property of the Hilbert space more than a property of a particular Hamiltonian. We have exact wave functions, exact revivals, and that means we can actually do a lot of things. We can measure anything we want in those wave functions, and we can manipulate them, move them inside the spectrum to different positions. So now we are at the position, I would say, where we have a toolbox, and now we are looking for, maybe with your help, for a great application, what we can do useful physically with it. So now I'm done under an hour. So,